Hi friend, welcome to Math A to Z. In this class, we discuss an important sector of number theory, which is linear congruence, and the most important theorem, Chinese remainder theorem. Now we start with the definition of linear congruence. What is linear congruence? An equation of the form Ax congruent to B mod n, called linear congruence. Linear congruence. Okay, where A, B belongs to Z and N also belongs to a natural number. Now, if x0 be a solution of the linear congruence, then we have Ax0 congruent to B mod n. That imply n divide B minus Ax0, right? Or Ax0 minus B imply there exists y0 belongs to Z, that is in the set of integer, such that Ax0 minus B equal to ny0. That is Ax0 minus ny0 equal to B. And in this equation, this equation is of the form Ax plus by equal to C. This is similar, Ax plus by equal to C, and this is the linear Diophantine equation. So the solution of linear Diophantine equation and linear congruence are equivalent. Okay, because here we get two variables, x and y, and the variable values are x equal to x0 and y equal to y0, such that Ax0 plus by0 equal to C. And here also we get x0 and y0, such that Ax minus ny0 equal to B. So we say that the linear congruence and linear Diophantine equation have the equivalent solution, or two equations are equivalent. Now we give here an important theorem related to linear congruence, or from this theorem we say that when a linear congruence have a solution and what is the number of solution. And the first theorem is if GCD of A, n, GCD of A and n equal to 1, then the linear congruence AX congruence to B mod n has unique solution. That is, the linear congruence have only one solution. Now, proof. Since GCD of A n equal to 1, so there exists U V belongs to Z such that AU plus NV equal to 1, right? Imply AUB plus NVB equal to B. Imply AUB minus B equal to NVB, and this imply AUB minus B congruence to 0 mod n, since here n, that is AUB congruence to B mod n. So we can say that X equal to UB is a solution of AX congruence to B mod n, right? Now we prove the uniqueness of the solution. Here we let, if possible, x1, x2 are two solutions of AX congruence to B mod n. Then AX1 congruence to B mod n and AX2 congruence to B mod n, because x1 and x2 are both satisfied the equation. That is AX1 congruence to AX2 mod n, because AX1 congruence to B and AX2 congruence to B. That is, we can write AX1 congruence to AX2 mod n. Imply x1 congruence to x2 mod n. We cancel from both sides a, because GCD of an equal to 1. So we say that x1 and x2 are congruent modulo n. That is, in view of congruence, x1 and x2 are the same. So there are no two solutions. There are only one solution. x1 and x2 are same. So the solution is U. Right? That is, if GCD of an equal to 1, then this linear congruence has unique solution. Now we go to the second theorem related to the number of solution and existence of solution of linear congruence. The linear congruence AX congruence to B mod n has a solution if and only D divide B, where D is the GCD of A and N. GCD of A and N. If D divide B, then it has D mutually incongruent solution modulo n. Okay, if D divide B, then it has the solution, and if D divide B, then it has D incongruent solution. Now, proof of this theorem. In the first part, we let AX congruence to B mod N has a solution X congruence to U or X equal to U. Then AU congruence to B mod N imply N divide AU minus B, or we take B minus A, similar. And we get D divide N, then we can write D divide B minus A, right? N divide this and D divide this, so D divide B minus A. Also, D equal to GCD of AN, that is D divide A, that is D divide AU, and D divide B minus AU from here, that is D divide AU plus B minus AU, sum of this and this, that is D divide B, right? So we say that if we take X equal to U be a solution of this linear congruence, then we must have D divide B. D divide B. So contrapositively, we say that if D does not divide B, then AX congruence to B mod N have no solution. Okay, and this is the first part of the theorem. Now we go to the second part. Here D divide, let D divide B, and since AX congruence to B mod N with D equal to GCD of AN, then we get A by D, X congruence to B by D mod N by D. This is the property of congruence. Since GCD of AN equal to D, so GCD of A by D, N by D must be 1. Okay? So this equation or this linear congruence have unique solution. We prove this result before this theorem. So this linear congruence has unique solution, say X congruence to X1 mod N by D. This is the unique solution. That is, we can write X equal to X1 plus N by D into T, where T belongs to Z, set of integer. and t assumes the value 0, 1, 2 to d minus 1. But the value of t are this 0, 1, 2 to d minus 1, we assume this value. So, by putting the value of t in this position, we get the solutions as x1 by n by d, x1 plus 2n by d to x1 plus d minus 1 into n by d. These are the d solution of this, and we name this as 2. Okay, and we name the equation right, we name this equation, this is 1 and this is 2. Now we have to show that the integers in the list 2, that is these d integers, are incongruent solution modulo n, but all the other solution corresponding to other value of t, that is t equal to z minus 0, 1 to d minus 1, t belongs to z set of integer minus this. Other value of t are congruent to some one of the listing value of 2. Okay, all the other value are congruent to someone of in the list of 2. Let we first from this 2 value x1 plus t1 into n by d and x1 plus t2 into n by d are congruent modulo n. So from the property of congruent we delete this and this, and we also cancel n by d, because t1 congruence t2 mod n by d, that is t1 congruent t2 mod d, right? That imply d divide t2 minus t1, but this is impossible since t1 and t2 both greater equal to 0 and less equal to d minus 1. So this is impossible. That is, we say that these two x1 plus this and x1 plus this are not congruent. These are incongruent. So we first prove all the d solution in the list 2 are incongruent modulo n. Now let Tj belongs to z minus 0, 1 to d minus 1, right? Then by division algorithm we get equal to D into Q plus R, where 0 less equal to D 0 less equal to R less than D or less equal to D minus 1. Then we can write x1 plus n by D into Tj equal to x1 plus n by D into dq plus R, that is equal to x1 plus nq plus n by D into R, and this is congruent to x1 plus n by D into R, because here n and here mod n, right? So we get that x1 plus n by D into Tj congruent to x1 plus n by D into R mod n, where 0 less equal to R less equal to D minus 1. That is, this integer belongs to the list 2, must be belongs to list 2, because 2 since because R belongs to Z and 0 less equal to R less equal to D minus 1. Here also Q, R both belongs to Z. That is, we say that if Tj is not 0, 1 to D minus 1, then this type of solution must be congruent to one of the solution in the list 2. So from this relation and the above proof, when we prove these D solutions are incongruent, we say that the linear congruence Ax equal to B mod n has only D number of incongruent solution modulo n. Okay, that is, if GCD of an equal to D, then D be the number of incongruent solution, and all the other solutions are congruent to some one of this. Right? This is very important theorem of linear congruence. The statement of Chinese remainder theorem is: let n1, n2 to nr be positive integer be such that GCD of n I n j equal to 1 for I not equal to j. Then the system of linear congruence x congruence to a1 mod n1, x congruence to a2 mod n2 to x congruence to ar mod nr has a simultaneous solution which is unique modulo the integer n1 into n2 to nr. This is famous Chinese remainder theorem. Before going the proof of this theorem, we consider two linear congruence equation in general form as 2x congruence to 1 mod 5 and 3x congruence to 9 mod 6. This equation can be written as 2x congruent to 6 mod 5, and this implies x congruent to 3 mod 5, since GCD of A means 2, 5 equal to 1, and divide 6, and from here we get x congruent to 3 mod 6 by 3, that is x congruent to 3 mod 2, that is x congruent to 1 mod 2. So we see that this type of equation, if they have the solution and they also, it transfer of the form x congruent to 3 mod 5 and x congruent to 1 mod 2. So we can take a system of linear congruence in general form as x congruent to a1 mod n1, x congruent to a2 mod n2 to x congruent to ar mod n. Okay, now we going to prove Chinese remainder theorem. First we consider n equal to n1 n2 to nr, the product, and let nk, capital Nk, equal to n by small nk for k equal to 1 2 to r. Then obviously nk equal to n1 n2 to nk minus 1 nk plus 1 to nr, and since GCD of ni nj equal to 1, I not equal to j, so GCD of nk nj equal to 1 also, because here nk is absent. Okay, sorry, this is nk, capital Nk by n, small nk equal to 1. So we can say that the linear congruence nkx congruent to 1 mod nk must have a solution, since GCD of a, that is nk, comma n, that is small nk, equal to 1, and 1 divide b, that is 1, this is b, must have a solution, and it has a unique solution. We know this by previous theorem. Say x equal to xk as the solution of this linear congruence. Now we consider x bar equal to a1 n1 x1 a2 n2 x2 to ar nr xr, and our aim is to show this integer x bar is the solution of the given system. This expression we consider, and our aim to show this expression or this integer as a solution of this system. We have ni congruence to 0 mod nk for I not equal to k, because n k divide capital Ni, I not equal to k. That is, we get x bar congruence to ak, nk and xk, and all the other term other than ak, nk, xk are congruous to 0, because for this argument mod obviously mod nk. Also we know nk xk, nkx congruence to 1 mod nk has a solution x equal to xk, that is nk xk congruous to 1. So we put this result here, x bar congruous to ak into 1 mod nk, that is x bar congruous to ak mod nk. Here k equal to 1 to 2 enough, and since in all values of k the integer in the left hand side are the same, that is x bar, so we say that x bar this is the solution of the given system of R linear congruence. Now we prove the uniqueness of this solution, because here statement says unique solution modulo n. This is, we consider n. If x dash be another solution of this system, then we can write x dash congruous to ak mod nk also, that is x bar congruence to ak congruence to x dash mod nk. Now nk divide x bar minus x dash, and this result is true for r equal k equal to 1 to r. That is, we get n1 divide x bar minus x dash, n2 divide x bar minus x dash to nr divide x bar minus x dash, that is n1 n2 to nr. This product also divide x bar minus x dash, that is x bar, that is n. This product is taken as n divide x bar minus x dash, that is x bar congruence to x dash mod n. So we say that x bar and x dash and x bar are unique modulo integer n1 into n2 into to r, that is modulo n. So this proves the uniqueness of the result, and this is the solution of the system of linear congruence by Chavez-Remainder theorem. Now we consider a simple example to apply this theorem. Now example as this is from the book Elementary Number Theory, David M. Burton, and the problem is x congruent to 1 mod 3, x congruent to 2 mod 5, and x congruent to 3 mod 7. Using Chinese remainder theorem, here a equal to 3 into 5 into 7, that is 105, and n1 equal to n by n1, that is 35, n2 equal to similarly 21, and n3 equal to this is 15. Now the linear congruence n1x congruent to 1 mod 3 n2x congruent to 1 mod 5 n3x congruent to 1 mod 7, that is 35x congruent to 1 mod 3, 21x congruent to 1 mod 5, and 15x congruent to 1 mod 7 all have unique solution, and they satisfy, or we know that the solution of these are respectively x1 equal to 2. Since if we put x1 equal to 2, x equal to 2, then 2 into 35, that means 70 minus 1, 69, that is modulo 3. Similarly, x2 equal to 1 and x3 equal to 1, and these are a1, a2 and a3. So the solution of the given system can be written as x equal to, or x bar equal to this is okay, this is a1, sorry, this is not a1 a2 a3, this is a1 a2 a3, a1 n1 x1, a2 n2 x2 plus a3 n3 x3 modulo 105, and putting the value of a1 means 1, 2, 3, a1 a2 a3, 1 into 35 into 2, 2 into 21 into 1, 3 into 15 into 1 mod 105, right? That is 157 mod 105. Sorry. That is 52 mod 105, and this is the solution of the linear congruence, system of linear congruence. Okay, this is our today's class about linear congruence and Chinese remainder theorem, and the PDF of handwritten note of this class, that is linear congruence and all the theorem of linear congruence, Chinese remainder theorem, and some example, solved example from the book David M. BURTON are given from the link in the description box. Okay, thank you for watching. Thank you very much.